Alright everybody, my name is Michael Tynski IV, and I'm going to be talking to you guys about Einstein's theory of general and special relativity. So, in order to build a little bit of a background, I believe it would be a good start in order to explain the state of physics at the time of Einstein. Now, at the time of Einstein, there are two major branches of physics. There was classical mechanics and gravitation, as invented by Sir Isaac Newton, which describes the motion of macroscopic objects, from projectiles to parts of machinery, astronomical objects such as spacecraft, planets, stars, and galaxies. And it insists that velocities are never absolute, but are always relative, so their magnitudes must always be appended with the phrase, "with respect to." The second major branch of physics at the time of Einstein was electromagnetism, perfected by Sir James Clerk Maxwell. It describes a type of physical interaction that occurs between electricity, electrically charged particles, and the electromagnetic field. It insists that the velocity of the electromagnetic wave, also known as light, is fixed no matter the frame of reference or medium of travel. This was a big problem for physics at the time, because at the time, physicists were under the impression that they had figured it all out. They had predicted the motion of the stars and the planets. They were able to discover this new and mysterious force of electromagnetism, and they thought that the sky was the limit. With all of their knowledge at the time, they thought that they can predict everything to happen if given enough information. But this fact that things, according to Isaac Newton, must be appended with the phrase, "with respect to," and James Clerk Maxwell saying that the speed of light is constant no matter what it's with respect to, was a major problem for physics at the time. But before we get more into that, I'm going to explain a little bit more about classical relativity. According to Isaac Newton, it is not enough to ask how fast something is moving. We must ask how something is moving relative to something else. Two people can observe the same event as being different depending on their perspective. The classical example is, imagine a baseball player standing on a moving truck throwing a baseball. If the baseball player throws the ball at 90 miles an hour, from his perspective, he will see the ball moving at 90 miles an hour. But to someone standing on the side of the road, they'll see the ball going at 140 miles an hour, because the ball also had the velocity of the truck added to it. Now, according to electromagnetism, it predicts that the electromagnetic force is carried by electromagnetic waves. It can travel through a vacuum, meaning it doesn't need a medium to travel through, and it always moves at a constant velocity, about 3 times 10 to the 8 meters per second, no matter the reference frame. This contradicts classical mechanics in that if things were Isaac Newton's way, it'd be the same as a baseball player throwing a ball. Anyone who's standing outside of the truck, if they were to turn on a flashlight, according to Isaac Newton, the speed of light would be 3 times 10 to the 8 plus 50 miles an hour. But James Clerk Maxwell argues no, it's not. It's always 3 times 10 to the 8th meters per second. No matter what, no matter where you're going, no matter where you stand, you will always measure it to be 3 times 10 to the 8th meters per second. This threw physics, the entire field, into chaos. You had a whole bunch of smart people trying to consolidate these two theories together mathematically, and trying to build an understanding of the universe with respect to these two ideas, and trying to nudge them and fix them together in such a way that they do not contradict each other. And the best way that they can come up with is to say that light, although it is suspected not to move through a vacuum, what if it moves inside its own medium, which is called the luminiferous ether? In order to consolidate both the theories of classical mechanics and electromagnetism, scientists theorized the existence of this ether. It was thought at the time that all waves must travel through a medium, such as waves in water, sound in air, etc. So it wasn't too far of a stretch to suggest that light itself must move through a medium. In order to consolidate both theories together, scientists said that this medium must exist separately from, but alongside the entire universe. And it was theorized to have contradictory properties such as being entirely rigid, yet flexible enough so that light can travel freely through it, but still interact with objects in our universe as it was known. Now, if this was all said and done, in the way that science worked, if science worked in that someone says something and it must be true, like philosophy, we would have been all set. But science demands experimentation. Here come Michelson and Morley. They determined that if this ether existed, it must have the same properties as if you were driving down the highway in your car. And you stick your hand out the window. You would feel some sort of resistance against your hand from the air. The Earth travels very quickly. It travels around the sun. And if the ether existed, the Earth moving through it would cause a wind, in the same way that there would be a wind outside of a car. Depending on where the Earth was and what season it was, the effects of this wind would be different. The speed of light would be different in the spring than it is in the fall. So they developed this experiment where they shot two parallel laser beams. No, perpendicular laser beams. And they perfectly synced them up such that when they were fired and when they reached here, they should be in phase with each other. And that the lights traveled the same distance, traveled the same speed, the same way. And if the ether existed, one of these beams would experience this wind, as if you were sticking your hand out the window and be pushed back slightly. Thus causing the two lasers to be out of phase with each other. At the time, this was one of the most rigorous scientific experiments conducted. They had the lowest margin of error from any scientific experiment conducted at the time, and they had flaming piles of grant money behind them to make sure that it was all right. They leveled these lasers in the most advanced way that they could. They made sure everything was accurate. They did all of their, they dotted their I's, they crossed their T's, they made sure everything was great. And it came time, they're like, all right, we're going to do the experiment. They turn it on, take their measurements, do their calculations, and then they realize there is no difference between the laser beams. Okay, well maybe our setup wasn't big enough. Maybe in order to know the small difference between the wind and the way it actually is, we need bigger lasers. So they built bigger lasers. Took up an entire warehouse. Same thing. Most advanced experiment ever conducted to physics at the time. No ether. Well, maybe we just need more flaming barrels of grant money. And we need to rent out land in the desert. They conducted the experiment with kilometers long laser beams perpendicular to each other. The most advanced ever done. Still no ether. Physics exploded that day. Something was wrong. Classical mechanics or electromagnetism was deeply flawed. And with the negative results of this experiment, the pieces had to be picked up and put back together in order to create a now valid theory of the universe, which this experiment has shown that we do not have. This laid the groundwork for Einstein at the time. He was working as a patent clerk. He was 26 years old and just graduated with a degree in physics. He was having trouble finding work in his field, and he was working as a patent clerk trying, in his spare time, to consolidate these theories. In physics, the theory of special relativity is generally well accepted and experimentally well confirmed. It regards the relationship between space and time. In Einstein's pedagogical treatment, it is based on two postulates. The laws of physics are invariant, i.e. identical, in all inertial systems, and the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source. Today it is the most accurate model of motion at any speed when gravitational effects are negligible, but even so, the Newtonian mechanical model is still valid as a simple and high accuracy approximation. This theory has a wide range of consequences, which have been experimentally verified to this day, including length contraction, time dilation, relativistic mass, mass energy equivalence, i.e. E equals mc squared, and a universal speed limit, the speed of light. Now, where was I? What Einstein decided to do was he decided to say, hey, Isaac Newton, James Clerk Maxwell, what if you're both right? What if the speed of light is constant? And what if things are with respect to one another? But what if you just got something wrong? What if the way that these things travel through each other could be different? What if the spaces that observers observe are different? What if the times that they observe are different? If you adjust things in such a way, you can come to an agreement. But you have to accept some pretty freaky things about the universe. This brings us to a thought experiment that Einstein conducted. According to his theory of special relativity, it's impossible to say that in absolute sense, two distinct events occur at the same time, if those events are separated in space. This is Einstein's train. Let me see if I can get my cursor over here. So, in this picture, there are two observers. There's a person sitting inside the train as the train is moving along at near the speed of light. Outside of the train, standing on the side of the train, where is my thing? There's another observer. Now in this picture, each thing, as you go downwards, is a different interval in time. So the first thing to happen is that two lightning bolts strike the front and the back of the train simultaneously. In the first unit of time that passes, the light from the front of the train reaches the observer who's moving near the speed of light. And they say, ah, a lightning bolt has struck the front of the train. In the third way down, light that has struck both the front and the back of the train reaches the observer, who is standing outside of the train. And he goes, ah, the front lightning bolt and the rear lightning bolt struck at the same time. And then the final thing, the observer on the train goes, ah, the rear lightning bolt struck. According to Einstein, it is possible to disagree on the order of events. It is possible for one observer to say that the lightning bolts were simultaneous, and it is possible for another observer to say that they were separated by some amount of time. This leads us to the strange and interesting phenomenon of time dilation. It's the difference between the elapsed time between two events as measured by observers. In Einstein's theory of relativity, there are two types of dilation. In special relativity, clocks that are moving run slower according to a stationary observer's clock. This isn't because the clocks are broken the faster you go, but it's because that is the nature of space-time. The second is that observers may be in positions with different gravitational masses. In general relativity, clocks that are near a strong gravitational field run slower than clocks in a weaker gravitational field. And as you can see here, this is the special relativistic equation for time dilation. And the reason why Isaac Newton and Maxwell at the time wouldn't have reason to believe in disagreements in time, is because we exist in a universe generally where every day-to-day things occur nowhere near the speed of light. As points in this is velocity of an object, and this is the dilation of time, the difference in time that things exist. It doesn't become noticeable until you're about 30%, 40% the speed of light. So at our day-to-day life, we would think that all clocks are universal. To help illustrate this fact, it is useful to imagine a clock. Now in this picture, this depiction of a clock, the clock works this way. If you have two mirrors, A on the bottom, B on the top, well, it doesn't really matter, and a beam of light that is traveling up and down between the mirrors. Anytime the light hits one of the mirrors, the clock reads 1 second. So tick, 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 tick. For the stationary clock, 1 second is 1 second. Things are normal. As you start to move the clock, weird things start to happen. This is the same clock. The lighter part is the clock. But as it's moving this way, different sections are at different times. So say that the clock is moving. Now it doesn't have to travel this up and down distance. Tick, tick, tick. No. The clock must travel this diagonal distance. Tick. Tick. Now from Pythagoras, we know that the hypotenuse of a right triangle is longer than its two composing sides. A squared plus b squared equals c squared. Thus, if you have any sort of motion between clocks, the clock must travel a longer distance. Not the clock. The beam of light between the two mirrors must travel a longer distance in a moving clock than a stationary clock. Meaning that since the speed of light is constant in all reference frames, a moving clock runs slower than the stationary clock. And this gives us the impression that time is different. Now, this is a real and observable effect, and it's probably helpful to do an example. For instance, if you had a spaceship that was moving at 99% the speed of light, and a year passes to the guys on the spaceship, how long would people on the Earth say that the spaceship was out in space? If you plug and chug, you see that people on the Earth will say that 7 years has passed. The people on the spaceship will say that 1 year has passed. This is a real phenomenon and has been scientifically confirmed. But that's not the only weird thing that happens because of relativity. Another weird thing that happens because of relativity is this phenomenon known as length contraction. The faster you move, the shorter objects will appear to you. Length contraction is only in the direction in which the body is traveling. For standard objects, this effect is negligible at everyday speeds and can be ignored for all regular purposes. It's only significant when the object approaches the speed of light. And I don't have the time to go through an example for this, but the faster you go towards the speed of light, the shorter things appear to become. Now this brings us to general relativity. Now Einstein had figured out special relativity in terms of non-gravitational frames of reference. So if you have fast-moving things in the vacuum of space or fast-moving things within short vicinity, that's Einstein's special theory of relativity. He had fixed Maxwell and Newton for everything except for gravity. Now usually that would take just one genius to do, and it would take one genius in an entire lifetime to do. A difficult task to fix all of physics. But Einstein is not a one-trick pony. Einstein created the general theory of relativity. It is a geometric theory of gravitation published in 1915, and it is the current description of gravitation in modern physics. General relativity generalizes special relativity and supersedes Newton's law of universal gravitation, providing a universal description of gravity as a geometric property of space and time, otherwise known as space-time. In particular, it's the curvature of space-time that is directly related to the energy or momentum of whatever matter or radiation is present. This theory has important astrophysical implications. It implies the existence of black holes and gravitational waves and other phenomena that we are now observing. Now, unlike Newton's theory of gravity, in which Isaac Newton says that if you have two bodies of mass, one body will exert a pull on another body, and it's that pull that is the phenomenon known as gravity. What causes that? No one has any idea. No one has any idea what causes that pull. But there's a pull, according to Newton. Anything that has mass has a pull. Well, Einstein says, wait a minute. What if there is no pull? What if the pull is an illusion, caused from the bending of the fabric of space and time in itself? We experience a phenomenon that we call gravity because we are experiencing a distortion of space and time in itself. And we are merely interacting with it, and our little monkey brains are not advanced enough to just calculate the laws of physics in a whim. Now, according to Einstein, masses bend the fabric of space and time itself, in which all things travel, including light. According to Einstein, you can get this effect known as gravitational lensing. Gravitational lens is a distribution of matter that is capable of bending light. Now, it is this effect that has confirmed Einstein's theory of relativity in the beginning. Back in 1919, an expedition was made out during a solar eclipse. Because as you can see in the top picture, if Einstein is right, and space-time is bent, and things can travel across bent space-time, if you have a mass such as the sun, and a star that is located behind the sun, and the star emits a light, that light will be bent as it passes close to the sun. As it travels through its distorted space-time field and reaches the Earth. If you follow that line from the Earth straight, that is where the people on Earth will say that that star is located. And this is the thing that allowed Einstein's theory to be accepted within the scientific community. Because in 1919, two separate expeditions were made out during that solar eclipse, and measurements were made, and it was confirmed that Einstein's predictions of the bending of starlight were accurate. Another effect of Einstein's gravitation is time dilation. But this time not because it's moving, but because of the presence of an accelerating object, or, the distortion of space-time in itself due to a massive object. Gravitational time dilation is a form of time dilation, and the actual difference of elapsed time between two events as measured by observers situating at various differences from a gravitational mass. The higher the gravitational potential, or the further away a clock is from the source of gravitation, the farther time passes. This has been demonstrated by noting that atomic clocks at different altitudes, and thus different gravitational potential, will eventually show different times. The effects detected in such earthbound experiments are small, with differences being measured in nanoseconds. But for objects in a slightly higher gravitational potential, this effect is significant. Not crazy, but it is significant. GPS satellites in geostationary orbit must take into account gravitational time dilation in order to give us accurate readings. If they did not take into account gravitational time dilation, they would be tens of kilometers off from their prediction or calculated GPS positions. GPS wouldn't work. Now, to explain why gravitational time dilation happens, it's important to understand freefall. Einstein is quoted as saying the happiest thought in his life was for an observer freely falling from a roof of a house, and there is during the fall, at least according to the observer, no gravitational field. Einstein really likes watching people fall off of houses. He really loves it. I don't know, something with that guy. Namely, if the observer lets go of any bodies and they remain relative to them in a state of rest or uniform motion, if you're falling, it kind of feels like you are in the vast emptiness of space. And there are planes that take advantage of this fact, and they're called zero-G flights. You buy a ticket, you gotta have a lot of money, but you can buy a ticket on these things and experience zero-G for yourself. Or at least an illusion of zero-G. Now, this helped Einstein kind of come up with the mathematics, which are a little bit past the scope of this discussion. But he came up with the concept that freely falling objects in a gravitational field will say that they are in a state of rest. So to explain this time dilation concept, I bring us once again to the clock. This time oriented in a vertical fashion rather than a horizontal. The top clock is the same as the left clock from before. It's stationary, it's not moving. Let's see if we can go. Every time it hits one of the mirrors, a second passes. Tick, 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 tick. The second's normal. But as you have a body in free fall, it's the same effect as a moving clock. It takes longer for the clock to fall down, well, the light in the mirror fall down and give us a tick. It's like kind of object inside of a gravitational field would feel this distortion. If you're in a gravitational field, your clock ticks slower. For the astronauts on the ISS, their time moves faster than time down here. They perceive time to be moving faster, or they see us in slow motion. The GPS satellites move faster than us. Now this is because of the way that mass interacts with space-time. Different objects affect space-time differently. And the more massive an object is, or more mass concentrated within an area, or a volume, probably four-dimensional, I don't know what that's called, space-time's weird, more pronounced of an effect that ends up happening. Space-time distortion near a sun is less exuberant than space-time distortion due to a neutron star and less than a black hole. Very strange things happen. Counterintuitive things. And I shall end off my presentation with a description of something that happens. Now, if you were with a buddy, and one of you were unlucky enough to fall into a black hole, how would you two view the world or the universe around you? From the guy outside looking in, he'll see his buddy falling. He's moving backwards and backwards and backwards. But as he gets closer and closer to the distorted field of the black hole, the effects of time dilation will become more and more pronounced. Since he's entering a very dense gravitational field, he will be appearing from the outside observer to be moving slower and slower and slower until eventually it would appear at a certain point that he just stops. Once he stops, the light that is emanating from him will begin to become more and more redshifted and less intense until he eventually, or she eventually, fades into obscurity. Probably the worst of the two, if you ask me. But from the person who's falling in the black hole, something beautiful happens. Ignoring that they experience a painful and violent death, and that they're probably screaming, and, well, they can't scream, no one can hear you scream in space. What they will see is their effects of time dilation will be such that when they look out, they'll see time moving faster and faster and faster. Until, in seconds, they are able to witness the birth of galaxies, the destruction of planets, and the entire life of the universe flowing through quickly, like on fast forward. Until eventually, in their final moments, they will see the end of the world. I think that's a pretty way to go. If we ever get that way, I choose that one. If I don't get shredded to pieces from a black hole. Now, Einstein's theories are very weird indeed. And things don't move the way that we think classically. For different observers and depending on our masses, time moves slowly, time moves faster. Time is not a universally agreed upon thing. Black holes exist, and lengths and distances are not agreed upon. But at least we have the beauty and understanding to realize that this is the true nature of the universe. And that the universe is very strange. Or maybe we're strange, and we just don't get it. This is one of the most well-confirmed and well-experimented theories in all of science. But yet, like in the days of Einstein, when there was a disagreement between classical mechanics and Maxwell's theory of electromagnetism, we face a similar dilemma. We face a similar dilemma in that the theories of gravitation as proposed by Einstein do not agree with theories of quantum mechanics. And there's still a lot of work to be done. These theories are new, and they're in their infancies, and we have a long way to go. But every day we make progress. And every day we're moving forward, and every day we're coming closer to understanding things. And it may be that our lifetimes are so insignificant that we can't comprehend it, or that the universe will eventually give in to entropy and decay far beyond the time that we can understand things, or maybe we can't ever understand things. The infinity of things to understand is probably larger than the things of infinity that we can record things on. Information is another instance. But we are here. And we do have what we know. And that's got to be at least something. Any questions?